In this video, we're going to be talking about heat transfer and starting to quantify how much energy is being transferred under different circumstances. So heat transfer is symbolized with a lowercase letter q. Note that the lowercase is important. Capital Q is going to be something else in a little while. And the first thing that's important to recognize is that when heat energy is transferred, the effect is not always the same. So the same amount of heat can be transferred and result in a different amount of temperature change. So the amount of heat required to cause a particular temperature change is going to vary by substance. And we describe the relationship between how much heat is transferred and how much the temperature changes using a quantity known as the specific heat, sometimes also referred to as the specific heat capacity. This is symbolized by the lowercase letter c, and this is the amount of energy or amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. When you're talking about temperature change, degrees Celsius and Kelvin can actually be used interchangeably because the size of 1 degree Celsius is the same as the size of 1 Kelvin. So if something increases by 1 degree Celsius, it's also increased by 1 Kelvin. If it decreases by 27.2 degrees Celsius, it also decreases by 27.2 Kelvin. So when we're talking about change in temperature, degrees Celsius and Kelvin are interchangeable. When we're talking just about one temperature reading, they are not. For absolute temperature, for not a temperature change, you need to be able to convert between the two. And Kelvin, so that conversion factor, to get to Kelvin is just degrees Celsius plus 273.15. Sometimes you'll see it as just plus 273, but more precisely it is 273.15. So the specific heat units is pretty much exactly what you would expect based on the definition. So specific heat is the amount of heat per gram per degree Celsius. So the only thing here that's going to be a little bit unfamiliar is the unit of energy. It's the unit of heat transfer, which is known as the joule. So you will see the units on specific heat described as joules per gram degree Celsius or joules per gram Kelvin. So the J stands for joule, which is the SI unit of energy. So 1 joule is a very, very small amount of energy. In chemistry, we usually work in kilojoules, in thousands of joules. In most chemical reactions, or many chemical reactions anyways, transfer energy in the hundreds or thousands of kilojoules per mole of reactant. So 1 joule is very small. We're usually working with very large quantities of joules being transferred. So specific heat is what allows us to relate the amount of heat transferred to the amount of temperature change for a given substance. So we have an equation that allows us to relate those two things, that allows us to figure out how much heat is required to cause a particular temperature change. So the relationship is Q equals mc delta T, where Q, as we've mentioned before, is the heat transfer in units of joules. M is the mass of your substance in units of grams. C is the specific heat, which we just talked about, in units of joules per gram degree Celsius or joules per gram Kelvin. And then delta T is the change in temperature. In either degrees Celsius or in Kelvin. Note that this is always calculated as the final temperature minus the initial temperature. The sign on it is important. If delta T is positive, it means your substance got warmer, the temperature increased. If delta T is negative, it means it got colder, the temperature decreased. So this is always T final minus T initial, not the other way around. So note the triangle here. It is very much a triangle, is a capital Greek letter delta. Wherever you see this in science, it means change. So you'll be seeing a lot of deltas in your life in this unit. So here we're dealing with change in temperature, but you'll start seeing this all over the place. So anytime you see this little triangle, it means something is changing. Delta T means change in temperature. So we can use this relationship to relate any of these 4 quantities. So for example, we can use this to figure out how much heat is required to raise the temperature of 55 grams of water from 20 degrees Celsius to 35 degrees Celsius. So we're going to be using the same relationship, and we can identify what do we know, what don't we know, to be able to solve this problem. So how much heat is what we're being asked about here. That is Q. So Q is our goal, is the thing that we don't know and want to solve for. How much heat is required to raise the temperature of 55 grams of water? So 55 grams is our mass. We're given the specific heat right here. Even told C equals 4.184. So you'll always be given specific heats that you need. You do not need to memorize them. Move this guy out of the way. We'll come back to that one. So the specific heat of liquid water is 4.184 joules per gram degree Celsius. That one will use a ton, so you will probably come to know it whether you want to or not, but you do not need to memorize it. And then delta T, we're not given directly, but we're told that we're looking to increase the temperature from 20 degrees Celsius to 35 degrees Celsius. So that is enough for us to figure out delta T. We're starting at 20 degrees, so that's our initial. We're going to 35, so that is our final. So delta T is always T final minus T initial. So 35 minus 20 is a temperature change of 15 degrees Celsius. And that temperature change is positive because we have increased the temperature, we've made our water warmer. So now it's just a matter of plugging in and solve. So the mass was 55 grams. The specific heat was 4.184 joules per gram degree Celsius. And delta T was 15 degrees Celsius. So that comes out to be 3,450 joules that would be required to put into this sample of water to raise its temperature by 15 degrees. So we can apply the same idea to a different situation, asking us how much will the temperature increase if 100 joules of heat are applied to a 10-gram block of silver at with a specific heat of 0.240 gram degrees Celsius, joules per gram degree Celsius. So in this one, same idea, same equation here. We're going to need this guy. In this case, we know the amount of heat that's being applied. We're told that 100 joules of heat is applied to this sample. So that is Q. We are told that it is a 10-gram block of silver. So we're given the mass. We're also given the specific heat. And then what we're being asked is how much will the, ooh, that's the wrong writing utensil, sorry. How much will the temperature increase? So we're being asked to find delta T. So using the same equation in a different way, just to solve for a different variable, we've got 100 joules, 10 grams, specific heat of 0.24 joules per gram degree Celsius, and then we can solve for delta T. So delta T comes out to be 41.7 degrees Celsius. So since the specific heat is much, much lower here, a relatively small amount of heat is going to lead to a relatively large temperature change. So one other thing to note when we're talking about heat is that the sign we use on Q indicates which way the heat is being transferred. So when Q is positive, when Q is greater than 0, means that heat was absorbed. When Q is less than 0, or negative means that heat was given off. You can also think of these rather than absorbed or given off as gained or lost, whatever works for you. But the sign that we're using on Q in both of these examples was positive because we were putting heat into the water and into the silver to increase the temperature. But if it was going in the other way, if these things were cooling off, we would expect the value of Q to be negative.